we're going to revisit our harmonic number example from last time. So we're visiting harmonic numbers. So last time, I had shown you that h of n, the nth harmonic number, which if I want to remind you, the nth harmonic number is equal to the sum from I is equal to 1 to n of 1 over I. So this is just 1 over 1 plus 1/2 plus 1/3 plus all the way up to 1 over n. I'm going to show you that h of n, the nth harmonic number, is in fact big O of log n, specifically log base 2 of n. But even then, that doesn't matter too much for us. Now, you might say, Dan, like we didn't talk so much about what the nth harmonic number, like h works. Like how does h work? So what I'm going to be doing is I'm going to presume that n is a power of 2, but specifically I could do also this. I can observe that the harmonic number, nth harmonic number, if I look at h as a function, I could tell you that h is asymptotically non-decreasing. It's asymptotically non-decreasing because of the following. Because, well, I'm just going to write out the definition again. 1 over I. This is going to be strictly less than the sum from I is equal to 1 to n of 1 over I plus 1 over n plus 1. But notice this is strictly bigger than 0, right? But what's this? What's this? This right here is just simply going to be equal to the sum from I is equal to 1 to n plus 1 of 1 over I. But this is just h of n plus 1. So this is true for all n greater or equal to 1. So that means that n0 in that definition for the asymptotic non-decreasing, you would be just 1. So that means that my finite harmonic series, or the nth harmonic number, if I think of this as function h, it is asymptotically non-decreasing. You could find n0 equal to 1 works. This is because when I add the next component, go to the next entry, notice that it's just going to be adding a positive quantity every single time, meaning that the quantity only makes it bigger, it never gets smaller. So it is asymptotically non-decreasing. So that means that we have, say if we're trying to prove, for example, that h is big O of log base 2 of n, then it has to be that f, which is our nth harmonic number, or h, is asymptotically non-decreasing. Log base 2 of n, we have already proven that that is smooth. So we have all of the conditions necessary to apply the smoothness rule. So we're going to prove, again, we're going to try proving this again, but we're going to do it in a more refined way. We're going to prove that h is big O of log base 2 of n. But this time, you're going to see I'm not going to need any bookkeeping. It's just going to be rather nice and slick. So you're just going to see I'm just going to purely apply the trick that I used last time. So I'm going to assume n is greater or equal to 1, because that's just the way these definitions work. N is greater or equal to 1 is a power of 2. This is very often how you could set up using the smoothness rule. Power of 2. Then here's what you can do. Then h of n is equal to h of 2 to the power of k for some k greater or equal to 0. And we also have the following property, that h of n is equal to the sum from I is equal to 1 to n of 1 over I, which is going to be equal to 1 plus 2, 1 plus 1/2 plus 1/3, plus all the way up to 1 over to the power of k, which this is just going to be simply h of 2 to the power of k. You can see right away, if you see my previous example, how much more slick this is. Because now I notice that I don't have to round up to the next highest power of 2 or anything like that. I just get it. I already am working at a power of 2. So now I'm going to lay out the game plan for the big O proof. So let me just head over here, okay? So we find constants. C, which is a positive real number, and n0, which is a positive integer, so that the following is the case. So that h n is less than or equal to c times log base 2 of n for all n greater or equal to n0. So now I'm going to employ the same trick I used before. So we're going to formulate that second series. So we're going to formulate a second series as follows. So you're going to recognize this from last time. So we're going to do this on the right-hand side. We're going to do this on the right-hand side. So I'm going to grab terms successively. I'm going to use the same trickery. This common technique you can use when it involves the harmonic series. So 1 is in fact less than or equal to 1. So I'm going to take each one of the terms I have there. I'm going to grab them by increasing powers of 2, the number of terms, and I'm going to bound it by whatever 1 over that power of 2 is. So I'm going to have 1/2 plus 1/3. These are the next 2 terms. This is all going to be less than or equal to 1/2 plus 1/2. Then I grab the next 4 terms, because that's the next power of 2. 1/4 plus 1/5 plus 1/6 plus 1/7. Notice it always goes up to, but not to the next power of 2. This is one nice design about how grouping them like this works. All of these are going to be less than or equal to 1/4. So I have 4 1/4. And you can keep doing this. Keep doing this. For each successive power of 2, so you'll have 1 over to the power of k minus 1 plus 1 over to the power of k minus 1 plus 1 plus all the way up to 1 over to the power of k minus 1. So the next, just before the next power of 2, like before, this is going to be all less than or equal to 1 over to the power of k minus 1. And this is going to be done to the power of k minus 1 times. So this is written this is written to the power of k minus 1 many times. And then I have my last term like before. 1 over to the power of k is less than or equal to 1 over to the power of k. So if you take this, remember everything here is h of n, which is now equal to h of 2 to the power of k. This is the second series which I'm bounding from on the above side. So I'm making everything on this side is going to be bigger or equal to whatever's over here. So I'm going to put that all together over here. So this means that h of n is equal to h of 2 to the power of k, right? We're not needing to do any rounding up, right? We always have it where they're equal like this. So we have 1 plus 1/2 plus 1/2, right? This is the right-hand side of that I formulated over there. So I have 1 plus 2 1/2, which remember this equals 1. Then I have 4 1/4. So if I keep writing out powers of 2, where it's 1 over that given power of 2, when I write it that many times, it's just always going to sum up to 1, right? So this keeps happening, right? And I have 1 plus 2 to the power of k minus 1. I write that 2 to the power of k minus 1 times. This is just going to be sum equal to 1. And then I have the 1 over 2 to the power k again. But remember, as we established last time, when you do this, it's just going to end up being equal to k. Because remember, this is 2 to the power of 0 to the power 1, 2, 3, all the way up to k minus 1. How many of these have I written? How many groups of these? There's k of them. Plus the last term, 1 over 2 to the power of k. But now, since I know that h of n is equal to this, I could just proceed as follows. So observe that for all n greater or equal to 1, h of n is less or equal to k plus 1 over 2 to the power of k, which this is equal to, remember, k here. You might say, okay, Dan, what's a k? Well, think about it. Think about it. In our example over here, we wrote out what that was. Well, remember when I wrote out the definition of a logarithm, right? I have 2 to the power 1, log base 2 of 2 to the power of 1 is just 1, right? Okay. Well, we have k. Well, notice that this would be, in fact, whatever log base 2 of n would be. If you're unsure about that, go back to the previous time we tried going through this, and you'll see that I'm just talking about the same thing. And remember, 2 to the power k is equal to n. So I have log base 2 of n, which it's really unclear, just remember what it would be. Remember, we know 2 to the power of k is equal to n. So I'll just draw it off to the side here. So I have n is equal to 2 to the power of k. So if I take logarithms of both sides, meaning I apply it to both sides, because these are equal to each other, so that's their logarithms must be equal if I take them on both sides. This will be log base 2 of n is equal to log base 2 of 2 to the power of k. There's a power law, which I'll be discussing one of the future streams here, or the lectures here. You'll end up with a k out front here, then you have log base 2 of 2. This is just 1. So that's where this comes from, if you really just need to derive it yourself. So that's where this comes from. But this is less than or equal to log base 2 of n plus 1, because 1 over n could never exceed 1, because n is greater or equal to 1. So now I have h of n is less than or equal to log base 2 of n plus 1. So I'm going to try using the same trickery I used before, but now I have a much smaller factor here, so I'm going to pick c is equal to 2. So I'm going to play lookalike. Then we need to find n0. We find n0 so that h of n is less or equal to 2 times log base 2 of n. So notice the following. So notice that when n is greater or equal to 2, we know that h of n is less than or equal to log base 2 of n plus 1, which remember we have that from up here. It's right here. Is less than or equal to log base 2. And we're going to use the same trick we used actually earlier on in the session. Log base 2 of n plus log base 2 of n, which this right here has to be greater than or equal to log base 2 of 2, which is equal to 1, right? For a sufficiently large value of n. In particular, it has to be the case when n is greater or equal to 2 because logarithms are increasing functions, right? Which this, in fact, is equal to 2 log base 2 of n, which that's the right-hand side. So we just choose n0 to be equal to 2. Choose n0 is equal to 2. And now what we do is we employ the smoothness rule. So we're going to employ the smoothness rule here. So the function log base 2 of n, remember we established this earlier on, is smooth. So log base 2 of n is smooth. So we're going to use, so this is us invoking the fact that log base 2 of n is smooth, so we're just going to use the smoothness rule here. Therefore, by the definition of big O, H is big O of log base 2 of n unconditionally. And we're done the proof. Now, hello. But yeah, no, so I have given you a much simpler version of the last example that we did last time. So notice that now there's no more bookkeeping. That actually simplifies and smooths out the analysis so we can focus on the fundamental technique here.